The output voltage is given as three parameters, half sine x plus 2x squared minus 4. And the inputs are cosine x, and positive 1 volt. This is a design problem using summing of M. So three inputs and it will give you different outputs, three parameters. If we look at the summing of M, it can have multiple inputs. And then you have to take the ratio of RF and R1, R2, R3 in such a way that the values and the signs, plus or minus, they are exactly as this one. Before that stage of V1, V2, and V3, which are three inputs, sine x, and plus 1 volt, you have to do some manipulation using integrator, differentiator, and then you see there's just 4. There is no other function, which means you have to create a gain of 4, either using an inverting op-amp or a non-inverting op-amp. If I do not specify the value of resistors or capacitors which you can use, there can be an infinite combination of answers. So it's better to specify some design constraint, especially in the exam. Maybe I will say use only certain value of capacitor or certain type of resistor. Let's look at the first input, cosine x. In order to make it a sine x, what type of op-amp circuit do we need? What type of op-amp circuit would you need? How do you get sine x out of cosine x? I'm not going to teach you mathematics. You should already know that. This is a second year course. So I'll just go ahead and do it. If you don't understand, it means the problem is with your mathematics, not my course. We spend a lot of time for unnecessary things in the class. If you take d dx of cosine x, you will get negative sine x. That's calculus. That's not from my class. How do you get x squared? Take integral x dx, you're gonna get x squared over 2. And 1 volt, how can you turn it to 4 volt? Maybe make a circuit with a gain of 4. So I'll bring you to a different screen and then you'll have to solve it. Let's go to screen sharing, change the screen. From now on, I'm not going to explain circuit theory or calculus or mathematics. That is your foundation. This course is second year electronic course. We have to focus on the core topics of this course, not some A, B, C, D or A plus B. No, not that one. Doesn't work that way. Maybe we should do on the class notebook. The whiteboard is kind of, I can possibly do on the whiteboard if it works. All teams. No, let's go to the whiteboard maybe. Can you view the whiteboard?
Yes, sir, we can see it.
Yes, yes.
Okay, inputs. What are the inputs? Cosine x. So, oh, that's quite thick. Maybe 4. This is cosine x. Cosine of x is one of your inputs. In order to get sine x, what do you have to do? d dx of cosine x. What is d dx of cosine x? negative sine x. And what is a differentiator circuit? For a differentiator circuit, capacitor comes first. Capacitor comes first, right? You have an op-amp. I'm going to provide in the inverting input. This is non-inverting. Ground. What is the feedback element of differentiator? Resistor. This is R. This is C. Because what is the output equation of the differentiator? Minus RC minus RC and then d dx of cosine x. What will you get on the output side? You're gonna get minus RC and d dx of cosine x is equal to negative sine x. Isn't it? We want half sine x on the output side. You can make it the product of R and C equals half. Or you can make the product of R and C equal 1. And then when you put on the summing op-amp, you can make it plus sign. This is already plus sign. But if you go to the summing op-amp, what happens if you have an inverting input? It will become minus. You want a minus sign? This is fine, but you want a plus sign at the end. This is not okay. Let me draw a summing op-amp. This is the last stage. Minus, plus. And then this is the final output voltage, V out. For the summing op-amp, you have a feedback resistor. And then you have an input resistor. It's up to you. Can we make a unity gain summing op-amp? Means everything is the same ratio. If I take here, let's say 2.2 kilo ohm, 2.2 k ohm, and this one is 2.2 k. So this is all, this is called a unity gain. The gain is 1. If R times C is 1, and then if you add this input here, what will you get? Minus sine x, isn't it? Sine x, and then goes again in the output side, it becomes minus sine x. So we probably need one more inverting stage in between, the unity gain inverting stage. Let me do that one. This is plus, plus, the bottom is plus. This is 1k. I just put a value. 1k, this is 1k. If R times C is 1, you have sine x here, and then output is sine x times minus 1. So minus sine x again times minus 1, you get total sine x. But what is our desired output? Half sine x. So R times C should be 0.5. You follow this part? Any questions?
Teacher,
Yes.
the C is a constant, right? I mean, like the number of the C.
If I say, if I don't say anything, you can pick any value of capacitor and any value of resistor that you want.
Oh, okay.
But to make things easier for checking and grading, maybe I say in this problem use only certain value of capacitor. What if I say C has to be 100 microfarad? If C is 100 microfarad, take C is 100 microfarad. What should be the value of R? Find out the value of R. What's the resistor value?
Yeah, I got like 5 times 10 to the power negative 3.
Is it negative 3?
5 kilo
Yes.
ohms.
5 kilo
It's 5
ohms.
kilo ohms.
It is 5K. If you take this capacitor as 100 micro, then the resistor is 5K. Now you take the output from this differentiator is minus RC times d dx of your input. D dx of cosine x is negative sine x. Minus and minus becomes plus, and then you go through another, unity gain inverting op amp. It becomes minus, and then finally you have to go to your summing op amp. Again times 1. RF is 2.2, R1 is 2.2K. When you flip 2 times the sign, finally you get half sine x. So V out here is half sine x. What was the other two parameters? Let's take the second parameter. The second parameter, the output should be 2x squared. Your input is x. Let me draw another input. This is x volts. How do you get x squared out of x? You cannot do d dx. You have to do integral, right? For the integrator, what do you have? You have resistor first and capacitor as the feedback element. Okay, let's analyze. This is capacitor. The second one should be a capacitor. I draw a resistor. What is the output equation from integrator? Minus 1 over RC times integral of x dx. Integral of x dx, what are you gonna get? If you take x integral, x dx integral, what do you get? X squared over 2, isn't it? And then there's a negative sign, and then you multiply by minus 1 over RC. This one has to be positive 2x squared. So what you get out of here is going to be negative, and then when you pass through the op amp, it will automatically become positive. I don't have to do another additional stage. If you take again C as 100 microfarad, let's say I force you to use 100 microfarad again for the second stage, what will be the value of R? C here is 100 microfarad. 100 micro. This has to be equal to negative 2x squared. It has to be equal to negative 2x squared. If you set the left hand side and the right hand side equation to be equal, minus and minus cancels out, x squared cancels out. So the equation is, what is the equation? RC equals 1 over 4. Is that the equation? RC equals 1 over 4. C
Yes.
is given. C is given. So what is R? 1 divided by 4C. That is R. How many kilo ohm?
2.5 kilo ohm.
2500 ohm, 2.5 kilo ohm. So this value is 2.5K. Now you do the equation. Minus x square over 2 over 1 over times 1 over RC. What do you get? It is actually negative 2x squared. After that, you have to feed it again. I already got in the form of negative 2x squared. I don't have to do anything else. I just have to multiply by minus 1. 2.2K here and 2.2K here. The ratio is 1. We are going through an inverting pin. Minus 2x squared times minus 1 becomes 2x squared. So we have the second one. Is there one more stage we have to do? Yes. What is the last input? The last input is positive 1 volt. What is the desired output? Let me write the desired output for you. You have to have negative 4. So think about it. If you have a positive 4 here, you multiply by minus 1, you will have a negative 4. If you want to have a positive output from an op amp, you cannot use an inverting one. Or you can use an inverting one, you have a negative, and then flip it again, make positive, and flip it again, negative. Maybe that's not the best way. Right? You can put 1 volt here with the minus pin, sorry, with the plus pin, and then I'm drawing now a non-inverting op amp. It's like this. Okay, this is RF feedback. This is R1. You want to get here V out equals 4 volts. What should be the ratio of RF to R1 in the green circuit? What is the output equation of a non-inverting op amp? V out equals what? 1 plus RF divided by R1 times V in. What do you need to get 4? 1 plus 3. Ratio of RF to R1 has to be 3. Can I just put here 3.3 kilo ohm because I have this in my lab? 3.3K. R1 is 1.1K. This one is R1. This is ground. Output voltage is plus 4 volt. You want to change it to minus 4. When it goes through the summing op amp, which is in the negative pin, it will automatically become minus. So what I will do here, I will just add another resistor. This will be, how much is the value? 2.2K and 2.2K. Ratio has to be 1. We're multiplying by 1. And then you have a complete output. Sometimes, especially during the online exam, you cannot draw online. The circuit is given to you, but I ask What is the output after the integrator? What is the output after differentiator? What is the output after the non-inverting op amp? And then what is the final output? I give you the solution, but I ask you what is the value of output at each stage? What are the value of resistor and capacitor? I can ask by that way as well. Let's say I already gave you an output. Tell me the value of resistor or capacitor. I'll let you have a look at this problem for a few moments and see if you understand, if there is something that you do not understand. If I, yes?
So in the green color, of and have RF, and where is
R1,
R1
R1. Okay, let me
off?
make it a bit clear, okay? It's kind of not very clean. Let me redraw it here. R1 and ground. This is R1. It is 1.1K. I took RF as 3.3K. This is RF. I took it as 3.3K to make the ratio 3. Why? The equation is 1 plus RF over R1 times V1. V1, V in is 1 volts plus 1. So 4 times plus 1 is positive 4. This is a non-inverting op amp. What you get out of this stage is going to be a plus sign. And then, because your problem says make the output like this, half sine x plus 2x squared minus 4 plus, when goes to the summing op amp again, plus 4 multiplied by what? Here is another RF over R3. Third one. This ratio is 1. We get minus 4. If you are given plus 4 in the problem, you could take an inverting op amp with the gain of, with the ratio of resistor is 4. So output will be negative 4 and then go through this is positive 4. Now we have to take ratio 3 because of the equation. It's not just RF over R1. You have a plus 1 term. Any other question? How about the integrator and differentiator stage? Are there any questions? Let me highlight. Here is 5K ohm, 100 microfarad. This one is 100 microfarad. This is 2.5K. Does everyone understand how to solve this type of design problem?
I think so. No?
Okay. We'll come back to our lecture slide then. You have to see the output and input. This is not the only problem of this type. I can change so many things. You just look at the output and input and see which one needs what type of op amp. Okay, here's another problem that we can do actually immediately on the screen. Determine the output voltage for the circuit below. What is the name of the first? Let me put some number. Let's call it stage 1. I circle it. What is the name or type of the stage 1 op amp? What do you call it?
Inverting.
Inverting op amp. Fine. Look at stage 2. This is a 2-stage amplifying happening. What can we call? What can we name the stage 2 op amp? It's an inverting op-amp. Inverting, yes, and summing. Summing op-amp, the input is given on the inverting side, inverting pin. It is adding two different inputs. One is coming from this stage 1, and this is from stage 2 itself. Or we can say this is 1, 2, and then this one will be 3. That is also okay. What is the output voltage at stage 1? Input is 12 millivolt. Feedback resistor 330 kilo ohm for stage 1. This one is input resistor. What's the ratio? Ratio of RF and R1. How many times larger?
10 times.
10 times. So you have 12 millivolt, it will be multiplied by 10 times. You get 120 millivolt, plus or minus?
Minus.
You're gonna get minus. So at this stage, if I put a voltage probe at this stage, let me clear a few things. At this stage, you are getting minus 120 millivolt. I can write that. MV. This one, still focus on the first one. Again, it passes through an inverting summer. What is the ratio of this feedback to the input stage resistor? How many times bigger?
That is 10 times too.
Again, so 120 millivolt becomes 1200 millivolt after passing through here. Plus or minus now? This is minus, it goes through another minus.
It will be plus.
Yeah, flip 2 times the minus, it becomes 1200. I did not write the unit, but it's millivolt. Just remember now it's millivolt. Now you can actually focus on the bottom one. You have 18 millivolts coming in, going through R2 and then RF. The ratio is again 10. So how much you get on the output side? $18 millivolt followed by this path.
180.
180 millivolt, plus or minus?
It will be minus.
It will be minus. So your total output is this minus this. How many millivolts is that? 1020 millivolts. I think it's 1020, isn't it?
Yes.
1020 millivolt means 1.02 volts. So final answer from this circuit, the final output is 1.02 volts, which is same as 1020 millivolts. Any questions about this one? Just a summing op amp, nothing else. So what do we have next? Some important parameters of the op amp. When you are operating the op amp with a closed loop feedback, it operates in a larger bandwidth. So in normal operation, it's a wide bandwidth amplifier. But some factors will affect the bandwidth of the op amp. One is called gain. How many types of gain did we study for the op amp? There are 2 types of gain. One is the open loop gain, which can be 10,000, 20,000, 50,000, usually 5 digits. And the other one is called closed loop gain. Once you add the feedback path, the gain becomes much less. It doesn't become few thousand, maybe it's 10, 25, something like that. Slew rate. Slew rate refers to another parameter which tells about the op-amp's ability to handle variation in signal. It's the rate of change in output voltage caused by a step change in the input. Here's the gain bandwidth effect. On y-axis you have the gain. Here in this case it looks like a voltage gain. Once the op-amp is open loop, AVD is called the open loop gain. That is the maximum, can be 20,000. By the way, this is a semi-log scale. This is linear, or maybe this is both log scale, possible. The frequency is definitely in log of base 10. Open loop, you have the maximum gain. Once you close the loop, see how the gain decreases. The gain becomes very less. But what happened in the open loop gain? If you take this is zero frequency, from zero to only this part, your amplifier can operate. That's a very small bandwidth, not really useful. You want to make the op-amp operate in a larger bandwidth. So there's a compromise. The compromise is make it operate as a feedback loop. Means as you increase the frequency, operating frequency, B1 here is the bandwidth. In this case, we are measuring from 0 to F1, so the bandwidth and the frequency, operating frequency, they are actually the same. FC is the center frequency. Let's say you're operating at this frequency. This is our center frequency. The gain has gone down a bit. It's now 70% of what you have. If you had 10,000, this is like 7,000. If you have 100, this is 70. But usually we have even less gain because from 0 to FC, bandwidth is still small. Maybe you want somewhere around this area. And the gain may be half times your open loop gain. It means that if you add in the open loop mode, narrow bandwidth not very useful, and if you want to make it useful, you have to close the loop. Gain is lower. You may argue that a gain of 5 or 10 or 20, it is much worse than the gain of 20,000. But in practicality, that type of gain is unstable as well. You cannot operate a stable circuit. Also, you can never have your input is 1 volt and output is 20,000 volt. That is going in the high voltage territory. Op-amp is a low voltage application. If you have, let's say, 0.1 millivolt and then you have open loop gain of 20,000, that's okay. You're going to get output volt of 2. That is within the tolerable range. But in real life, our circuit input is not half millivolt or 0.1 millivolt. To operate in the real life, you have to think of realistic terms, realistic values. Slew rate was the next parameter, sometimes shorted as SR, the maximum rate at which the op-amp can change the output without distortion. So delta of output voltage over delta T. Delta is the difference of two levels of output voltage, and delta T is the time difference during which that is happening. And this output change has to take place without distortion. If you have an input sine wave and then the output is also the same shape, the signal is not distorted. But if your output becomes like this is not the pure shape. The shape has been corrupted. We call it the distorted shape. Any shape that is not same as the original shape is a distortion. So the maximum rate at which the op-amp can change the output, but no distortion, we can call it the slew rate. Typical unit is voltage over microsecond. It happens very fast. This data usually is given on the spec sheet of an op-amp. Maximum signal frequency. Before you saw the slew rate. The slew rate also determines what is the maximum possible frequency the op-amp can handle without distortion. It is determined by this equation, slew rate over 2 pi times the peak voltage. Vp is the peak voltage. Your frequency has to be equal to or less than this value. If your frequency is larger than that, then the output can be distorted. We now can look at some spec sheet examples of op-amp. Other than the basic parameters, you can have some absolute rating, electrical characteristic, and performance. What are some of the absolute ratings? These are maximum ratings, very common for op-amp. Usually plus minus 22. Op-amp, you also have to provide a DC bias. There are 2 pins. The op-amp does not come as the shape of a triangle. It comes inside an IC. So there are pins for plus and minus voltage. You can add a supply voltage, typically within plus minus 22 volt. So the range is 44 volts. Minus 22 to plus 22, the range is 44 volts. Internal power dissipation, how much power it can handle before breaking up, 500 milliwatt. So this is almost half watt. Differential input voltage. What is the difference between the supply voltage and the differential input voltage? Differential input refers to V plus minus V minus. The difference between the plus pin and the minus pin should not be outside of this range. That is the differential input. It can operate in 3 modes, which I told you in the first class of op-amp. What are the 3 input modes of a differential amplifier? Do you remember?
Again, what did you ask again, please?
Given that you have a basic differential amplifier, what are the input modes? What are the possible input modes of a differential amplifier? Single-ended. So one pin is input, the other is ground. We call it single-ended. The second one is called what? Double-ended. 2 pins have the input, but they do not have the same polarity. One is plus polarity, the other one is minus polarity. And the third input mode is called common mode. Exactly the same voltage and same polarity is applied to both the plus and minus pins. So ideally they should cancel out on the output. 3 input modes. Okay, the next parameter is input voltage, means how much voltage you can provide at any of the pins, inverting or non-inverting. Should not be more than this. If you take the maximum values, let's say plus 15 for the V plus and minus 15 for the V minus, what is the differential? V plus minus V minus, it is positive 30. Supply voltage and input voltage, they are not the same. Supply voltage refers to the DC bias, which will turn on the op-amp. Input voltage is actually at the V plus and V minus. And the differential is the difference between them. Some other electrical characteristics. This is called micro A741. This is one of the op-amp models. It says how much VCC you can get, plus minus 15. And all the characteristics were calculated and determined at room temperature 25 Celsius. So what do you see? A lot of parameters here. CMRR, one of the most important one. Let's see what is the common mode rejection ratio. Between 70 and 90, and is given in which unit? Decibels. So it is 20 log base 10 of AD over AC. That's how it is calculated. It's not giving a ratio, it's giving in decibels. Total power dissipation, how much it can handle? Only 85 milliwatts for this model. Specific circuit conditions. If the operating temperature becomes 35 Celsius, I don't think you can use 85 milliwatts of power. You have to use a power derating curve. Means how much power you have to decrease for each degree Celsius in temperature increase. Sometimes the data sheet have this type of graph. The voltage gain versus VCC, power consumption versus VCC. You have to look at the units of the y-axis and x-axis. What is the input resistance for what frequency? Look at the input resistance. It's around, oh, this is also a log scale. Maybe this is 5 mega ohm. Op-amp is a very high input impedance circuit. That's why the current doesn't go from plus pin to minus pin. And also look at the output resistance or output impedance. Only a few hundred ohms. That's ideal. Any questions about the previous few slides? We'll look at some of the applications of op-amp, some additional applications. I'll take a quick washroom break, about 1 minute, then I'll be back. In the meantime, you can actually look at these graphs. I'll be back in a minute. All right, so I'm back. Any questions or any confusions about what we have studied so far for today?
Don't have right now.
Then we can move on to the next one, I think. Op-amp applications. Some of the common op-amp applications you see. Constant gain amplifier. We already seen this. You can make a gain by using either inverting or non-inverting or even summing of amp. You can do control sources. This is what we will talk about next. There are two types of sources in the circuit mainly. One is a voltage source. The other one is a current source.
Hold on.
And then the sources can be both independent and dependent, like controlled by something else. What is an independent voltage source? If I ask you, Can you give me an example of an independent voltage source in the circuit or in the lab? Do you remember anything that you have seen as an independent voltage source? Have you seen the DC power box in our lab? Any of you?
The DC power supply?
Yes. That's an independent source. In a circuit, the DC power supply, independent. It provides a source by itself. Of course, you have to adjust it, but it is not controlled by something else, if you think. And then the control source is, let's say you are getting an output voltage from some other source in the circuit, but that's a dependent source. If you kill the independent source, the main source, there will be no output from the control source. So that is dead as well. Similarly, you can think of the DC power supply as a current source because it provides a DC voltage, yes, but it also gives you a current. If you think in terms of current, it's a current source as well. So it can be independent or dependent, which is controlled. We have two types of voltage sources here we will study. Voltage controlled voltage source means it's a voltage source, but it is controlled by another input voltage. And then you have current controlled voltage source. The output is treated as a voltage source, but it is controlled by an input current. Then you have another two, current controlled current source. The output you treat as a current source because you are getting an output current, but it can be changed by another input current. Then you have voltage controlled current source. So the output is a current, but the input is a voltage which can also change your output. We'll later on look at active filters and instrumentation. But before that, we can have a look. I think in the BJT chapter, we talked about these multiple stage gains. If you have multi-stage op-amp, one, here is an example of three stage, 2, 3. What is the total gain of the system at this point? You just take the gain of each stage and then multiply. That's the overall gain, A1 times A2 times A3. Why the equation is like this in the bottom? As you can see, the first one is inverting in non-inverting pin input. So it's 1 plus RF over R1. The second and third stage amplifiers, op-amps, they're both getting input on the minus pin. That's why the equation is minus RF over R2 and minus RF over R3. But I can change the arrangement. I can make this first one in the last one. So the last stage gain, you have to see which input, plus input or minus input. The idea from this slide is when you have multiple stages, you just find gain of each stage and then you multiply. That's the total gain. Here are the list of control sources which you can use, which you can accomplish by using op-amp. When you go to the circuit, actually nothing has changed. The hardware has not changed at all. What has to change is the way you look at it. Let's look at the voltage control sources first. This is a voltage controlled voltage source. Okay, inverting or non-inverting, you can see it's a non-inverting amp version. Input is on the plus side, the inverting pin is grounded. What is the output equation? We know, we derive it, V out equals 1 plus RF over R1, and missing a letter on this slide, you should correct, times what? V1. If I simplify this equation, what happens? V out, if the resistors is fixed, so I can say V out equals K times V1. Can we write like this? Possible? Yes. This output voltage you can feed onto the other part of your circuit. Maybe you're doing a project. You're using this V out as a source to some other stage. So this is a voltage source controlled by an input. The resistors are fixed. I can change input voltage V1, maybe 10, 20, 15, according to my wish. This one becomes voltage controlled voltage source. The controlling parameter is V1, which is a voltage. The source, voltage source, which is the controlled, is V out. Can you have an inverting op-amp version of a voltage controlled voltage source? Of course you can have. What is the usefulness of this one? Why would you need a non-inverting voltage controlled voltage source? If you want to use a positive voltage to feed to somewhere else in the circuit or your project, you should use non-inverting. Sometimes maybe you need a negative volt to feed somewhere else. Then you can use inverting op-amp version. What is the output equation? Again, V out equals minus RF over R1 multiplied by V1. So V out equals, this is a fixed ratio if you don't have variable resistor, K V1. If you change V1, V out will also change. So again, you're having a voltage source which is controlled by another voltage. Voltage controlled voltage source. Any questions about this one? No questions? Fine then. What is the next source on our list? We did voltage controlled voltage source. What was the next one on the list? Voltage controlled current source, you think? Are you ready to go to the next part?
Yes.
Yes.
Okay. Did anything change in the circuit? Nothing changed. I told you what has to change is your way of looking at it, your perspective. You saw output voltage is gain times input voltage. Now, see, when you provide an input voltage, what is happening? You have an input current here, I1. You know this is a high input impedance amplifier. So I1 does not split and go inside the op amp. I1 will go purely outside with the feedback resistor. This is the load resistor, or maybe you can write RF. I1 equals I out. And then you have V out. What is I out? Okay, what is V1? Can you find the equation of I1 here? I1 equals V1 minus what? This pin. V minus divided by R1. Isn't it? And then another assumption, V minus equals B plus. What is B plus in this circuit?
0 volts.
0. So this equation I1 becomes V1 over R1, and I1 equals I out. So you can say I out equals V1 over R1. If I say 1 over R1 equals K, so it is the format of the output equation is I out equals K times V1, where K is 1 over R1. Or you can say I out equals V1 divided by K. That is also okay. Now see the output current. Output current is some constant multiplied by input voltage. So it is a current source controlled by a voltage controlled current source. Here you are getting output voltage, but maybe you design the circuit in a way that you are not concerned about the voltage. You are concerned about the level of output current I out. So instead of looking at voltage, you are now thinking about the current. The circuit hardware configuration, nothing changed. What changed is your perspective. You just rearrange the equation, and then you are expressing in terms of current. This I out, maybe you need 5 milliamp. I just give you a number. Maybe you need 5 milliamp for the next stage of your circuit, and maybe you want to change it to 10 milliamp, so you will double your V1. So this, now we are looking at a voltage control current source. Similarly, the next two on the list are current control voltage source and current control current source. So instead of looking at an input V1, we will look at things in terms of input current. Next one is current control voltage source. The left hand side of this circuit is not shown, but we know that there is an input V in here. You cannot have current without the supply voltage. On the left hand side of this side, there is an input voltage. We know high input impedance, input current I1 equals output current I0. And if you look at Ohm's law, I0 equals I1, this voltage is I times R, but we have an inverting pin, so you have to use the minus sign. V out equals negative I1 times RL or RF. There's some inconsistency here. One equation says RF, the other one is RL, but this is the feedback. There's an R1 hidden on the left hand side. So if you see this equation, V out equals, I can rearrange, V out equals K, or I can say minus K, times what? I1? Yes, this form. Output voltage is a function of an input current. It has become a current controlled voltage source. Any question? This part is clear? Do you understand this part?
Yeah.
Teacher,
Yes.
they have two formula, right? So depending on the equation, right? So we
It all
use either.
depends on the equation.
Okay.
If you want to imagine this as a current controlled voltage source, on the input side, you change to current. If you want to imagine as a voltage controlled voltage source, everything is expressed in terms of voltage.
Okay.
And the last one on this control source list is current control current source. This actually looks a bit more complicated, but it's the same thing. What is happening in this part? We call it the current divider rule. So if you look at I0, it is I1 plus I2. The directions may be changing if you point a probe inside. And I2 is I1 times R1 over R2. This is the law of branch current. I2 is not I1 times R2 over R1. In the branch, if you want to find the branch current, you have to multiply by the other member of the branch, not the self member. It is different, it is opposite of voltage divider rule. So anyways, this is the output equation. I out equals I1. You take a common 1 plus R1 over R2. And then 1 plus R1 over R2 is a fixed value because we did not use variable resistors. So I out is something multiplied by I in, I1. I1 is here. I1 will not go through the body of op amp. Again, the reason is high input impedance. This is a current controlled current source. I'm going to give you two circuits now. Just try to see if you can solve it. We're gonna go to the whiteboard. Let's go to the whiteboard. Everyone still can see the whiteboard?
Yes, I do.
Yes, we can see it.
I will go to the right of this thing a bit. Let me draw a circuit, all right? Thickness 4, let's use a pink one. Let me put a minus pin and then the plus pin. I will ground the plus pin with a resistor 2K. And then let me create something, an input resistor. I will have a voltage source, maybe. This is the voltage, plus, minus, let's put 8 volts. Input resistor also 2K ohm, and I have to put a feedback resistor. Let's call this 4K ohm. This is input voltage V1. And this current that will pass through the first, before going to the feedback, maybe I put the name I1. Maybe I put, this is the load because this is the output side, V out. Also we can say I out or I load. Let's call it I out. So calculate the load current or output current I out. What is the value? If you forgot the formula of voltage control current source, you can simply analyze the circuit. How do we analyze it? Can you find the value of I1? What is I1? V1 minus V minus divided by 2K. What is I1? And V minus has to equal to V plus. What is I1?
I got 4 milliamp.
You get 4 milliamp. So 8 divided by 8 volt divided by 2 kilo ohm. 8 minus 0 over 2. It's 4 milliamp. Yes. Correct. I1 equals I0. I0 then 4 milliamp. If you change the input voltage to 16 volt, what will you get? From 8 volt now you change to 16 volt, what will you get? You're gonna get 8 milliamp. You double the voltage, you will double the current, 8 milliamp. So this is voltage controlled current source. You change the voltage, you change the current amount. What about V out? I have not asked you about V out. If I ask about V out in the first case, everything is the same. What will be V out?
16 volts.
16 volts, positive or negative?
Negative, minus 16.
Minus 16 is an inverting one. So the ratio of feedback and input resistor is 2. 2 times 8 is 16, and then once you are inverting, because you're inverting, you get minus 16. So it depends. You are trying to solve the voltage or current. That's how you look at source. Let me draw you another figure. A new one. Minus, plus, and then I'm going to ground the plus pin. Again, I'm using an inverting because inverting is most common, also my personal favorite. Here, instead of voltage source, I can draw the symbol of a current source. In the circuit, a symbol of a current source is like this. This is input I1. I did not draw the resistor. It is 20 milliamp. Okay, it should have a resistor here. And then you have a feedback resistor. This is V out. The feedback resistor is 2 kilo ohm. This one is 1K. I just pick a value. What is V out? How much is V out? Is the question.
Negative 40.
Negative 40 volts, yes. Because I1 is same as I out. It will pass like this. If you use the Ohm's law, V equals I times R. This is the load resistor as well. The feedback is also the load. So the current times resistor, 20 milliamp times 20 kilo ohm. Milli and kilo cancels out. You have 40, but also be mindful of the pin assignment. It is negative 40 volts. So V out is a function of input current. If I change now, I want to 30 milliamp, you're gonna get negative 60 volts. If I change to 10 milliamp, you will get negative 20 volts. You are changing the voltage by means of an input current. This is what is happening. K I in. It is a current control voltage source. Previously, what you saw on top, it was voltage control current source. The V out question I asked additionally. So is that part clear, the control sources? Maybe you have this type of thing in the assignment. I could start a new subtopic, but we still have one more class to deal with this. And if you look, I'm going to show you on the screen something. Files, instructions for taking the quiz next Tuesday. Please make yourself familiar with the instructions. Everything is given. We have been using this for so many semesters now. It will be done by a Google form for the quiz. It is posted for you so that you can actually go have a look. Back to the whiteboard. I'd like to ask you about another circuit. Since we have a few minutes. So that you understand the operation of the op-amp. Very small, tiny area. Okay, zoom in and then let me draw another circuit. What should I use? Orange. Thickness 4. I will draw a circuit just random. I'll put here minus, the bottom is plus, and then the output is V out. I will put a feedback resistor here, an input resistor there. Let's call this input voltage V1, this one is RF. This one we will call the input resistor
That's
Rin.
R1.
Or I just call Rin. This is a different circuit. Just have a look. And then on the plus pin, I don't ground it. I will put another input. Let's call this one V2. And then I'll put another input resistor. So Rin is equal on both sides. If it's 1 kilo ohm on top, it's also 1 kilo ohm on the bottom. Here I will put another RF. So the
That's
top
actually
RF.
circuit.
What was the question?
Oh, nothing, Chair.
Yeah. RF and RF, they're equal. Rin and Rin, they're equal. What will be the output equation of this circuit? Let me zoom in a bit. This is a double-ended input. You have input on both pins, but not the same voltage, not the same polarity. I mean, same voltage, can be same voltage, V1 equals V2, possible, or different, but the polarity is definitely different. Because one is the plus pin, one is the minus pin. If you have a double-ended input like this, you always consider, for the case of output, you have to consider this thing. The differential voltage is like this. Vd equals V plus minus V minus. This is operating in differential mode, not common mode. So V out will be V, what is the voltage at V plus? V2 minus V1 is on the minus pin. Did we forget something? Times the gain. What is the gain? The gain factor is the ratio of feedback and input resistor. Now it is not 1 plus RF over Rin. That is only for the non-inverting single-ended op-amp. This is double-ended operation. So the gain equation, the gain ratio is common for both of these inputs. So take the differential voltage V2 minus V1, which is V plus minus V minus, and then multiply by the ratio RF over Rin. This is the answer for this circuit. It is not on the lecture slide, but it is quite useful. Sometimes you go on the second subject. My subject is called engineering electronics. The next step Jan Amulia teaches, it is called electronic circuit design. Even though it's not taught in this slide, the list of slides, you may encounter this circuit frequently. An op-amp with differential inputs. This is the equation.
Teacher?
Yes.
Like, do the whiteboard will stay in there?
Yes, it is like the whiteboard in the class, but you know, there's a problem with the design of this Microsoft team. So if you imagine your classroom, we have only one whiteboard, right? Whatever I write in 1 week, next class it is erased. I cannot add multiple whiteboards. I can rename,
Yes.
remove. Oh, expand is now here. I see, I was looking for it. I can rename or remove, but I cannot add more board in one class. Otherwise, I have one whiteboard for every day. So this is like your class whiteboard. At some point, I have to erase. But if you request me, if you want to copy paste all these things, I'll keep it for a week. Or I can actually go in the bottom. Another design problem of this whiteboard is the space here is infinity. In the class, the whiteboard is just some dimension. This one, you can go for infinity, and later on when I try to come back and find something, I cannot find anymore. I'll keep it like this until we do it until the quiz, okay? Maybe op-amp is not in the quiz, but I'll still put it like this until we finish the quiz one, and then I have to erase it. Also, the setting of the whiteboard is such that other students can edit now. So maybe I call some student to draw a circuit on the board. You can draw from your gadget and every one of us will see what is happening. It's interactive. Or you can take a snapshot. Maybe try this one. Can you see my screen, what's happening? Export as a PNG file. I normally use the JPEG format. This one is PNG. Standard resolution, high resolution. You can export, create a picture file, and then save on your gadget for later viewing. But once you export, you cannot edit that one. You can edit only on this screen. The next topic was about filters, high pass, low pass, and band pass using op-amp. That will be for our next lecture on Thursday. I am still looking at your assignment submissions. I already gave you solution number 2. You can look at it. I still want to look at a few more students, and then I'll select all and hit return. This is how I view it. As a teacher, this is how I view it. Can you see my screen?
Yes,
Can
sir.
everyone see my screen? So I see who has turned and who has never submitted. Based on that, you get a score or no score. And then to return, I have not returned it to you. Sometimes I put a comment, sometimes I will say, see the solution. So I click here. If I click return, all of you will get back your electronic file and this list will be empty. I still want to look at a few students and see if they are doing the right thing. So by the end of this week, I can return electronically. So back, Teams. I'll now make the attendance call. Mr. Balan,
Yes, sir.
Thirawut,
Yes.
Napatra.
Yes.
Pakon went to vaccine with his family. He has asked permission. Rajay,
Yes, Achan.
Tonikan.
Yes ค่ะ
Tonikan, are you in my lab class?
Yes ค่ะ
Last 2 times you are absent. Is there something wrong?
Yes. I cannot my internet it not work ค่ะอาจารย์
So please go to the recorded video for review. We covered a lot of important topics.
ค่ะค่ะ
Michelle,
Yes อาจารย์
Phil,
Yes, sir.
Silicon,
Yes
Wisalut,
Yes.
Yu Cheng, Mr. Yu Cheng,
Yes, teacher. Yes.
Sisi Han,
Yes, sir.
Patompong,
Here, how?
Gongsu,
Yes, sir.
Martin,
Yes, John.
Kolawit,
Yes, sir.
Pichayut,
Yes, I'm here.
Jinma,
Yes, sir.
Chonyuan,
Yes.
Satawat,
Yes.
Yapeng,
Yes.
Seni,
Yes.
Siripok,
Yes, sir.
Pitu,
Yes, sir.
An, San An here? Maybe not. Waramet,
Yes.
Hey, teacher,
Nabao.
did you call me?
Who?
Krisanapong again.
Sanan?
Krisanapong.
Not yet, Kisanapong, not yet.
Oh, okay. I thought you called me. I just came from the
Naba
toilet.
one. Naba one. Miss Naba one. Natapop.
Yes, I'm here.
Warapat.
Present, sir.
Nataya.
Yes, teacher.
After Nataya, we have Pichayapong.
Yes, sir.
Komchan.
Komshan here, sir.
Piladon.
Yes, I'm here.
Kisanapong is here. Is San An here? Mr. San An.
Chan is here, but he's have mic problem.
Okay, thank you. I'll give that him. Atitya.
Yes.
Hasi.
Yes.
Sukaina.
Yes, teacher.
Sirin.
Yes, teacher.
Min Luin U. Min Luin U, section 555. Not here. Okay. See you on Thursday.
Thank you, teacher.
Thank you,
Thank
sir.
you.
Thank you, Ajahn. Thank you, sir.
Okay, welcome everyone.